electrostatic conductors. Firstly, what is the meaning of conductors? Anyone? Yes. Yes, what is conductors? Hmm. The conductors are the material through which current can flow. Current can flow. That means what? If current can flow, that means electron can flow. So conductors are the material through which electron can flow. Right? Now, we'll see the theory part first. See, these are mobile charge carries in the there are mobile charge carriers in the conductor. There are some charge carriers which are responsible for the motion of electron. These charge carriers in metallic conductor are electron. The outer valence electron in metal separate from the atom and have free motion. The outer valence, that is the nth shell, the last shell, this last shell have an electron, this electron, if this electron removes and if this electron starts moving, then this electron is responsible for producing what? It is responsible for producing, yes, current. Although these electrons are free inside the metal, but they are not free to escape. The free electron produces a kind of gas colliding with one another and the ions and moving in the random direction. They produce different kind of gases when they collide, and they collide with each other and they form ions and they move in the random direction. And next is they travel in the opposite direction of external electric field. Yes, they will travel in the opposite direction of external electric field. Next is the positive ions, which are made up of nuclei and bound electron, remain in their fixed places. The positive ion, which are made up of nuclei and bound electron, they will remain in their fixed places. And the charge carriers in electrolyte conductor are both positive and negative ions, and their movement is influenced by both external electric field and chemical force. The charge carriers in electrolytic conductor are both. It can be positive, it can be negative, and their movement is influenced by both electric field and even the chemical force. Let's notice some important points. I'll give you some important points. First, I'll discuss your important point. Then we'll see what is written in our notes. First, I'll give you the summary of the point which we are going to. First, we'll give you the introduction of the point which we are going to discuss. First thing, let's understand few important points. First important point. First important point is a conductor has no electrostatic field inside of it. Inside the conductor, there are no electrostatic field. Just a minute. Give you some example for this. Yes. Electrostatics of the conductor. In the conductor, first point, in conductor, the charges will always lie Charges will always lie on the free surface. First, I write the point. Charge always lies on free surface. Always lies on free surface. Okay. Then second point, electric field will always be perpendicular to the surface. In in conductor, electric field will always be perpendicular to surface. Okay. Third thing. Third is the interior of conductor the interior of conductor can have no excess charge in the static situation, can have no static charge no static charge inside conductor. I'm just giving you the first point, then we'll discuss, then we'll have a deep dive into this point. Fourth point. Fourth is electrostatic potential is constant throughout the volume of conductor. Is constant throughout the volume of conductor. Okay. Then we then electrostatic potential is constant throughout the volume of conductor and have same and have same value on its surface. Okay, just remember this few important points. First point is that it always lies on the free surface. Second is, in the conductor, electric field will always be perpendicular to surface. Third point is, the interior of conductor can have no static charge inside conductor. And fourth point is, the electrostatic potential is constant throughout the volume of conductor and same value on its surface. Now, let's see each points one by one. First, it is given that a conductor has no electric field inside. Yes, a conductor has no electrostatic field inside. Then now, let us imagine a neutral or a charged conductor. When external electrostatic field could also exist in a static case where there is no current flowing through it or on its surface, the electric field is zero everywhere inside the conductor. This fact may be regarded as one of the unique characteristics of conductor. Force and drift would be felt by free charge carriers if the electric field was not zero. Let's see the next slide. Second point, the charge conductor, second is a charge conductor surface, electrostatic field must be perpendicular to the surface. A charge conductor surface, electrostatic field must always be perpendicular to surface. Electrostatic field would have some non-zero component along the surface if it weren't normal to it. Then free charge on conductor surface would encounter force and move. Electrostatic field should consequently not have tangential component in the static condition. Since this is the case of electrostatic field at the surface of charge, conductor must always be normal to the surface. If if the thing is, we are considering, see what was mentioned, it was mentioned that it will be always perpendicular. If let us consider it is not perpendicular, it is this or this, it will have a bad influence on the charges which are on the conductors, and it will start moving abruptly. Therefore always to so therefore always remember that our electric field is always what, it is always perpendicular to the conductor. Next, in a static environment, conductor interior cannot have excess charge. We have checked this point. Yes, in a static environment, conductor interior cannot have excess charge. So in a very tiny volume or surface component of neutral conductor, there are equal number of positive and negative charges. When the conductor is charged, the excess charge can only exist in a state of static on the conductor surface. Gauss's law predicts this. Take into account any volume element of a conductor on the enclosed surface that encircle the volume element V. The electrostatic field will be what? It will be zero. As a result, there is no overall electric flux across S. As a result, according to Gauss law, S has no net charge. Okay, let's see the next one. The conductor volume has constant electrostatic potential and its surface also has same value as inside. Moving a small test charge within the conductor on its surface does not involve any work since E is equal to 0 inside the conductor. But on the surface, there is no tangential component. That means there is a zero potential difference between any two spots inside the conductor surface. If the conductor is charged, an electric field perpendicular to the surface will exist. As a result, the potential at surface and at a point exactly outside the surface will what? It will differ. So each conductor in system of conductors of any size, shape and charge arrangement is defined by constant value of potential. However, this constant may vary from conductor to conductor. Okay, then we have electric field at charged conductor surface. We saw this formula. Yes, where we have saw this formula? Yes, in the first chapter. What was the first chapter? Saw this formula on the first in the first chapter. What is sigma? Yes, what is sigma? Surface charge density. What is epsilon naught? What is epsilon naught? Permittivity of free space. What is this n cap? This is a unit vector. What is epsilon naught? Epsilon naught is, yes, it is permittivity of free surface. Okay, then we can derive the expression for electric field. We can derive the expression for electric field at charged conductor surface. For that, what you will have to do, you'll have to choose a pillbox. You'll have to choose a pillbox, a short cylinder, as a Gaussian surface around any point P on the surface to obtain the result. Part of pillbox is inside and part is outside the conductor surface. It has minimal height and has a modest area of cross section delta S. The electrostatic field is zero just inside the surface. We have discussed this point. Electrostatic field is zero inside the surface. It has electric field, a charged conductor of a magnitude E, and is normal to the surface just outside. Sorry, I repeat the point. The point is the electrostatic field. This is from the diagram. The electrostatic field is zero just inside the surface. It has a magnitude of E and it is normal to the surface just outside. So these are the consideration, these are the points you are going to write when before starting the derivation. So as a result, only pillbox outside a circular cross section contribute to the to the overall flux through it. This is identical to E delta S. Since E and delta S are parallel or anti-parallel through the tiny area delta S, E may be regarded as constant. So the pillbox include the charge sigma delta S. E can be represented by charge sigma delta S. And we know what is E. What is E? Yes, sigma upon what? Sigma upon epsilon naught. Sigma upon epsilon naught. So we obtain the vector connection which holds true for both signs when we take into the account that fact the electric field is normal to the surface. So the electric field is perpendicular to surface inward for 0 and perpendicular to surface outward for 0. Inward it will be 0 and outward it will be 0. Next is shielding. What is the meaning of shielding? Yes, to protect something. Shielding means to protect something. So the fact that the electric field inside the cavity is 0, regardless of cavity size and the form, the conductor's charge and my external field in which it may be positioned is a surprising result. All charges only exist on a conductor's exterior. When it is charged or when an external field induces charge on a neutral conductor, any cavity in the conductor stays shielded from external electric impact, no matter the arrangement of charge and field outside, because the field inside the cavity is always zero. We call this as electrostatic shielding. Okay, then Just simply make this diagram. In this diagram you have an oval shape center, that is here E will be 0, sigma 0. Once more, we have this. Practice with me. Okay, here positive charges will be deposited, here negative charges will be deposited. Here positive charge, here voltage will be constant, inside voltage is constant. So if you say V or you say V naught, it will be what? It will be constant. And in between this, more thing will be constant. What? Sigma. Sigma will be what? Sigma will be 0. Sigma will be 0. And same, there is no potential difference, therefore you can represent it by V or you can represent it by V naught. Okay, you can simply make this diagram and you can write this points for shielding in electrostatics. The effect can be used to shield delicate instrument from external electrical interference. The effect can be used to shield delicate instrument from an external electrical interference. An overview of significant electrostatic characters of conductor is shown in the figure. See, electrostatic field is 0. See, our density is 0. And our potential difference will be what? That this will be constant. Okay, now question is, select the first question and let me know the answer. The question is, a positive charge conductor is what? The positive charge conductor is what? The positive charge conductor is, option A, is always at positive potential. Option B, it is never at potential. Option C is never at positive potential. Uh, D, it may have potential then positive, 0 or negative. Let me know. A positive charge conductor have what? It have put a positive potential. It does not have positive. It does not have potential. It never have positive potential. Yeah, it may have potential. That is, it can be positive, 0 or negative. Yes, the option is option A. I explain you. I give you the point that the charge conductor will have or will always have. Yes, it will always have positive potential.